different molecules that they appear in. So this bond association energy is going to be a tiny bit different than this one, but we can't, I mean, I'm not going to make us memorize or know when to use which ones all the time. So what bond association energies are is they are averages between every bond, despite, no matter what where it appears in a molecule. So we use these, but they're not always going to give us exactly the same delta H that maybe a Hess's law example might give us. So we just have to say these are averages, because this bond association energy, take that one apart versus that one, because it's way more complex. They're going to be a little bit different. Does that make sense? Okay, so how would I do this? I would be taking the bond association energy of the reactants minus the bond association energy of the products. Who are the what bonds in the reactants am I breaking? Okay, so a C to C double bond. Okay, what else? How many? How many C to H bonds are there, though? 4. So 1, 2, 3, 4. So I have 4 C to H single bonds that I'm going to break. I'm just listing out which values I need to find, essentially, because these are not the values, these are just the identities. So I've got 1 C to C double bond, I've got 4 C to H single bonds, and 1 H to H single bond. All right. So here are my reactants that I need to break, minus my products that I'm forming because they are releasing energy. What's the first one you see? So 1 C to C single bond, okay. And how many of the others? C. 6 C to H's. 6 C to H bonds. All right. You see that we just have to add up all the products minus the summation of the the summation of the reactants minus the summation of the products. And that's it. It's just these values have to be published someplace. I have those values for you. So in a book, you would find this. You would see 413 kilojoules per mole, and this is kilojoules per mole of double bonded C bonds. So it's like a mole of these types of bonds. And then you have 4 times the CH bond is, oh, I just lied. Mine's in a different order on my paper, sorry. All right, the C to C double bond is 614. You're back?
Yeah, I'm staying after school.
Okay, this C, we didn't get very far. Okay, we just wrote down all the bonds we saw. And so there was 1 double bond, there were 4 C to H single bonds, and then there was 1 H to H single bond, and then over here we have 1 single bond between C and C and 6 C to H bonds. And then these values are out of a book, and I have the book right here for you. Okay, so this one is 614 kilojoules per mole of those bonds, 4 times 413 kilojoules per mole of those bonds, plus that little one. Do you think it's gonna be? Well, I won't make you guess because sometimes it's hard to guess. This is actually 432, which is a little different than that one. Kilojoules per mole of this H to H bond. Okay, so there's all my reactants minus my 2 products. I just want to note that, yeah, this C to H bond and this H to H bond are both single. You can see they're very close to number 413, 432. The reason the H to H bond is actually harder to break is because H's and H's are smaller. So they get together really, really closely. And so their nuclei are more attracted to each other's electron clouds, and so it takes a little bit more energy to break them. I was supposed to be videoing anyway for Jordan, so somebody's got to catch Jordan up on that very first part. Okay, so C to C single bond is 347. You see how it's less, way less, almost half from the C double bond. Kilojoules per mole plus 6 times C to H. What's the C to H number? 413. Sometimes you can simplify these things before you plug these numbers in, but I usually just put them all on my calculator because I don't want to accidentally cancel something out I shouldn't, because you can mess yourself up that way. So, like, truly, I could say, okay, I've got 4 CH bonds here and 6 CH bonds here, so I would only be subtracting, what, 2 really, or adding 2 over there really, subtracting an addition of 2. So you can make that work for yourself, but I just commonly just do my calculator because I trust my calculator. It's my friend. Okay, you good with this? Oh, the answer is, thanks, negative 127 kilojoules per mole of ethane is our delta H of reaction. So you got so many tools in your toolbox for calculating H of reaction. Now we're going to use H of reaction to calculate other things. Okay? So I might be able to get this done today. Might not. I'm going to check, 4 through 7. You guys are going to do 8 through 11. We're not going to do it right now in class, but we're going to do entropy. So we've got to go through entropy because next week we're off 2 days. So, one day. Okay. Yay for these. We're done with that part. Yay. Let's do thermodynamics. Does anybody have a reference sheet with them? If not, go grab the white reference sheets. Somebody get up and go over there. Stand up for a second, stretch. So I'm going to show you where these equations are on your reference sheet too. Stretch with it.
I feel like an old person now. I'm supposed to speak for every hour. What do you wear? My costume.
Are you going to the meeting?
No. I'm having it.
Oh. You weren't even invited. I don't want to.
You okay?
You were so concerned about that one student that was sleeping back there, and I was like, no, he's just not caring. That was typical. The crutches, though. That was funny. I thoroughly.
Okay, you guys ready? I'm going to point out some things on your reference sheet before we begin so that you feel a bit more comfortable with this, because you get your reference sheet on the entire exam. You can see, there's some stuff for equilibrium on the left-hand side. We've not gotten to that yet. There's some pH stuff we haven't talked about. You see your gas laws? You see the gas laws in the reference sheet? They're on the upper right-hand side. So you get some gas laws, not all of them, not the hard ones, unfortunately. You get your gas law constants over there. You see the thermochemistry ones, Q equals MCAT. You see the delta H is equal to delta H of summation of products minus delta H summation of reactants. And you see S's and G's. What does S mean? Look to the side. Entropy, not enthalpy. Enthalpy is like thermal stuff. That's temperature, heat. Entropy is what we're going to talk about today. And then what does the G mean? Free energy. Okay, and how are they related? All three of those relate to one another. Which equation concludes them all? The fourth one, the delta G is equal to delta H minus T delta S. Who's ever seen that before? The fifth one, actually. Delta G is equal to delta H minus T delta S. Alright, and if people in my class saw it, you may not remember it, but you saw it. Okay, so, first law of thermodynamics, we are aware of this. This is something you already know, right? You know energy that's in the system will be equal to the energy that is transferred to the surroundings, because you can neither lose heat nor create heat. It is just 100% transferred. So energy lost from something is going to be redistributed elsewhere. Overall, the energy of the entire universe is constant. And it's hard to talk about the universe without talking about the parts of the universe, but we do have to talk about, we have to reference the universe a lot. Yes, ma'am. You do not have these. You are taking these. Yes. You do not have these. That's why I left this extra for a little bit. Or you can listen and copy notes later, or just listen. I'm recording right now. I don't think I passed it. If you're a listener, you're a listener. I rapidly take notes like it's nobody's business when I do this. I think I'm videoing still. I have to make sure. Yep, sure am. Okay. Hey, Jordan. Okay. So this is something that you need to know. There are 3 laws of thermodynamics, though. So that's, we already know the first one. We've experienced it before. Okay. Second law of thermodynamics relates to entropy. What letter represented that? S. Delta S to be specific. Okay. Entropy is a measure of disorder. So, who feels like my room has higher entropy than Mr. McNeil's room? His room is pristine, and I don't have enough time for that. So it's just a mess other than that, and I'm okay with that. So my room is very disordered compared to other teachers' classrooms, because learning happens here, and it gets messy. Okay, it just happens. So the entropy of the universe, this is the law. This is the rule. You cannot break this rule. Thermodynamics says that the universe's entropy has to be constantly going up, increasing, getting more disordered. Because overall, the universe is including everything. The universe allows for systems to become more disordered. There we go. What? It says disordered. It's disordered. Okay. There we go. So if entropy, delta S, or S, is a measure of the disorder of a system, then we would say that the system should be increasing in disorder, allowing for the overall universe as a whole to increase in disorder. So an example of that could be taking something from a solid state to something to a gaseous state. Because how is that representing disorder? A solid is a nice, cute little box with all the atoms in a line, and they're connected to each other, or they're bonded to one another, or they're attracted to one another. The gas is crazy, and they're bouncing off the walls, and they're hitting each other, you know, kinetic energy, elastic collision, stuff like that. So this is very ordered, and this is very, you know, disordered everywhere. So that's one example, and we're going to hit some more with in terms of like chemical reactions. That's just a physical change. So the reason that we call the solid ordered and the gas disordered is something called positional probability. Positional probability of being in different places. So the solid really has like those few places it can be. The atoms can be in maybe a different location, but not really. They're pretty well stuck to a specific location in the solid. But a gas has more positional entropy because they inherently are able to be here, or here, or here, or here, or here, or here, or here. And so those, whatever, 8 gas molecules I drew, they can all switch places like 16 times. Something like that. That's statistics. Probability. But inherently, gases have more volume. Therefore, they have more places they could be. So they have more entropy overall. More disorder overall due to the positional entropy. Positional entropy. Oh, there was something I was going to tell you in the last slide. Oh, no, it's still on the slide. The word spontaneous. To you, what does the word spontaneous mean? Like, oh, she's really spontaneous. Just goes out, does whatever she wants. He's spontaneous. Random. For us, spontaneous means occurs without intervention, without outside intervention. So spontaneous means it just happens. Stuff happens. It just does it all by itself. Without outside intervention. Yes, my room is very disordered, isn't it? Okay. So it just happens all by itself. So that's one thing that we're going to talk about. Because some reactions, you got to give them a little push to get started. You got to give them a little over the big hump. So that would be us trying to give the reactions, you know, energy to meet activation energy, and then they happen. So some things can happen without us doing that. Catalysts can actually help with this as well. Okay, do not write all this down. I want you to just look here. This can get really complicated. We're only hit like the highlights here, but there's entropy of the universe, there's entropy of a system, there's entropy of the surroundings. That's what it says. Okay. And this is really similar to like heat or enthalpy that we talk about, where the system and surroundings can add together to be the entropy of the disorder of the universe. So commonly we'll increase the disorder of a system so that we can increase the disorder of the universe overall. And so there we go again, spontaneous process that occurs without outside intervention. The only other part I wanted to tell you is sometimes they'll ask you to calculate just the entropy of the surroundings or the system, either one. And what they'll do is they'll want you to use this equation. We don't use this too often in class, like really rarely, but just in case I want you to know that equation. And it's not on your reference sheet. Delta S is related to heat and temperature, so Q and temperature. It's actually very, very well dependent upon temperature. So the disorder of something is equal to negative Q of the system over T. And the reason that I have the system is because the surroundings in the system are inherently related, but one is losing, one is gaining at all times. So if I leave the delta S of the surroundings of the positive number, it's the opposite for the system, so the negative of the system. Okay, notice though, what are these units going to be? What is Q? Kilojoules or joules, so I'm just going to put joules for now. And temperature? degrees Celsius for thermo, right? So a lot of times it's going to be listed as degrees Kelvin. I'm sorry, joules per degree C. You also can have joules or kilojoules per Kelvin. The temperature units for this one sometimes will vary. Actually, more often than not, you'll see Kelvin. This is now we've done thermochemistry, we've done Q equals MCAT, we've done enthalpy. That's about it for thermochemistry. Now we're hitting thermodynamics, which is like the last half of thermo, because we're including a lot more dynamic stuff like disorder, other forms of energy. And so then we kind of go back to using our standard units, which would be Kelvin. It's fun. Okay, so thermo's a little harder because we do switch back and forth between units commonly, but this is going to be very apparent when to use it because commonly this will be given as Kelvin in the problem. Okay, so the third law, first law is conservation of energy. Energy is, loss is equal to one that's gained. System and surroundings. Second law was disorder increasing for the universe. Third law is we have to identify something as a baseline for entropy, because entropy, like, when is something going to be so disordered? Like, who decides when something is too disordered? There needs to be a baseline about what's ordered and what's disordered. So what we say is very ordered is a perfect crystalline structure. So perfect crystal at absolute zero, so 0 Kelvin, has 0 entropy. Everything that we determine from there, we base it off the perfect solid, crystalline solid being 0 entropy. Oh, I have to tell you something else too. Oh yeah, I'll write it down here. This means all free elements, like in our previous experience with free elements, we said, oh, free elements have a 0 for their enthalpy. Since free elements are not perfect crystalline solids at 0 degrees or 0 Kelvin, we cannot assume that the free elements in this case with entropy are going to be 0. So we're going to say they're non-zero integers. They're non-zeros. So they are going to have some sort of value. It might be, chlorine might have a delta S formation of, I don't know, 400 joules per Kelvin. That might be what it is. I have no idea. But it's something non-zero. That's not 4. It was a 24 and 1, okay? So that's something important to know, that you cannot assume that they are free elements are going to be 0 in this case. So this is serving as a baseline for everything. So everything else should have more entropy than this, because this is the perfect solid. All right, so you can see some of the positional entropy stuff that we talked about previously. Oh my gosh. Okay, so you can see that a perfect crystalline structure has all the atoms arranged in a row. The positive and the negative of each end of the polar molecular part of it, in this case, are attracted to one another. Temperature is going to severely affect entropy, because temperature, what is the definition of temperature in Kelvin? Definition of temperature in Kelvin, up here. Temperature with Kelvin. Kinetic energy, thank you. Average kinetic energy. Do you need me? Okay. Average kinetic energy, as you increase temperature in Kelvin, it's going to increase the average kinetic energy. So then things start moving more and moving out of their little perfect world over here into a disarray. So temperature is going to severely increase the entropy. So entropy is very dependent upon temperature. Keywords, depend upon temperature. And then you can see that here with states. Ordered state, disordered state. This is an example of solvation. So ordered solid in its lattice form, and then dissolving. Do you remember this from your pre-lab for the thermo hand warmer lab you did? It said dissolving has to be, for something to dissolve, there has to be a driving force. Either it's very, very exothermic, because that's releasing heat, so the chemicals are left more stable, or they increase in their disarray, their disorganization, which they are in a dissolving process. So it has to be one or the other, or both, because if neither of that happens, then the reaction is called a no reaction and will not happen. So dissolving is definitely going to be increasing in entropy. Okay, these are some more examples of increasing in entropy. Melting a solid, because you're going from solid to liquid. so that there's more positional entropy. Boiling a liquid, going from liquid to gas, you're increasing in positional entropy. And then you can see my little scheme there. Solids have way less entropy than liquids, and then therefore gases. Dissolving does have, these are all increasing in entropy, increasing in entropy. Dissolving a solid, take a stab at it, increasing in entropy. Raising the temperature, increasing in entropy. Okay, you got like 4 more, maybe 8 more slides here. Yes, ma'am. It's because it's saying a gas is way greater in entropy because they have so much space to move about. Their positional entropy is like severely, or that's not the word, extremely larger near to liquid. All right, I'll give you guys a second there because these are some good examples. Like it might say multiple choice question: which of the following are increasing in entropy? And you just have to select. These are all phase changes for the most part here, and then the rising temperature could be with anything. Okay, with this, okay, so these are phase changes mainly. We're going to have some chemical changes as well. Give me an example of a chemical change that would be increasing in entropy. Combustion. Commonly, you have a nice little liquid, we'll go with pentane, or propane. Liquid propane and a gaseous oxygen. It's going to make a lot of gases like carbon dioxide and water. So commonly you have combustion. I don't have combustion on. Yeah, I kind of do. Combustion of sulfur dioxide here. But you can measure the amount of entropy based on the moles of gas present. Because gases have so much entropy inherently. If you have more gases, then you're commonly going to have more entropy involved. So this is just a decomposition of calcium carbonate. This is a solid with little entropy. This is creating a solid with low entropy, where the gases themselves have high entropy. And then you can see from reactants to products, 0 moles of gas to how many moles of gas? 1 mole of gas, right. In this case, 1 mole of gas for this first example. So therefore, increasing moles of gas would yield increasing entropy. For the second example, how many moles of gas? 3 moles of gas to 2 moles of gas. So what would you say overall? Decrease in entropy for this one. The first one was an increase in entropy. Yes, ma'am.
What if you're doing 2 gases at the same temperature? How would you know which one is more entropy?
You might, if the gases are different in their complexity, like if it's carbon monoxide versus, I don't know, something with a lot of C's and a lot of O's and a lot of H's, so something more complex, I would say the more complex one would have more disorganization, more disorder, more entropy. That's the only way you would be able to tell us, like the complexity of the molecule. Good question, because I think that's on one of your problem sets. Okay, can I move on? Thank you guys for dealing with me. Okay, so commonly, like we did with our enthalpy, you can actually get values out of a textbook, and you can find the same values, but for entropy, and you can do S of products minus S of reactants. What does this little knot thing mean? Standard conditions, like 1 atmosphere, 1 molar. Those are your standard conditions again. And so that is definitely what we would be using for SO formation. So I don't think it's in the book. It actually says SO formation. The book is over here on the floor. Oh, mixed one. Words are very bad. I don't think the F is there. I want to write it. It's not.
Very bad.
Not the index, but like the appendices. It's next, so like on the top of the. Oh no, go back. Does it say F's and S's on those? Not F's. H's and S's. So. Okay, so this, if you know how we had Hess's law, we had all your equations and you flip them back and forth, you could do the same thing with this to find the overall S of our entropy of reaction. You can do entropy of reaction with S products minus S reactants. That's about the only way you'll be able to find entropy though, because these are going to be measured values from initial entropy to final entropy. It doesn't matter what goes on in between. It doesn't matter how we get there. It doesn't matter if there's 5 reactions that occur or 1. That's what the definition of state function is. So I want to make sure we're clear with that. So what if I had products that ended up having high entropy, higher, minus reactants that originally started with lower entropy? What would that yield for us? Positive or negative number? Positive number. So think about it. Was it favorable or more likely to occur when you went from low entropy to high entropy, or high entropy to low entropy? High to low means that the universe is getting less disordered, because you went from a high disordered environment to a low disordered environment. That was not what was favored, right? You want to increase the disorder because it's leaving the system actually sometimes being more stable. So this is actually a good thing, okay? So the reactants to products being low entropy to high entropy, that's what this represents. So I'm taking the products minus reactants. This is great. We want the system to get more disorder, because in the end the universe gets more disordered and we satisfy the second law of thermodynamics. Great. Okay, so having a positive S of reaction is a good thing. Okay, that is favorable. Favorable is a word that we're going to be writing down a lot. If I give you another example of where we end up starting with high entropy in the reactants and ending with low entropy in the products, it would be opposite. So you'd have low entropy minus high entropy, yielding a negative S of reaction, and that's less favorable. That commonly will yield a reaction to be, not going to occur spontaneously anyway. So not occur spontaneously. So in the end, we would say that would be unfavorable for the universe if that happened. We're always trying to satisfy the universe, whatever that is. That is the end goal in chemistry. Can we do an example? I have a couple more examples actually. So rule of thumb, this is what we just wrote down. I'm going to come back up there in a second. Entropy, or any reactions that are increasing in entropy, are going to be yielding a positive delta S, and that is favored. That partnered with an exothermic reaction means that the overall reaction probably always happens spontaneously. So if you have a positive delta S and a negative delta H, the reaction will be spontaneous. Most likely. Temperature is still a factor when we're going to consider that momentarily. And to say something is spontaneous does not relate any information at all about how fast a reaction occurs or how quickly it's going to react. It's just going to say it's going to happen without outside intervention. If you set a old Chevrolet truck outside in the rain, it's not going to rust the first night, maybe not the second night, but maybe in a year it's going to rust. Okay, the oxidation of that metal is going to happen, and that is a spontaneous reaction, but it's going to take forever. Okay, so the rate of the reaction is not something you can relate to the spontaneity of it. So the definition of spontaneous means what? Without outside intervention, right? Without me going, rust truck, rust. Willing it to, okay? It's going to happen by itself, and it doesn't matter how fast it is or how slow it is, it's just called spontaneous. So that first statement is what I just explained there. Okay. Spontaneity is related to enthalpy, related to entropy, but it has a word that goes with it, or a letter, a variable that goes with it, called G, which is called Gibbs free energy. This is our third and final one that we're talking about. So the definition of Gibbs free energy is this random thing called energy available to do useful work. So it definitely relates back to the overall internal energy we talked about, because that was related to work. But we label it delta G, or G. I'm gonna give you guys a second here because the exergonic and the exergonic thing here is very important. I'm gonna let you guys write that down too. You guys can just read it. I'm videoing, so just read it. I was going to tell you something on the back page before I move on. What two conditions did I just tell you were favorable for reaction to occur spontaneously? Two conditions.
Positive and negative.
Okay, so positive entropy and negative delta H or negative enthalpy, right? So if a positive delta S and a negative delta H are always going to be spontaneous, what would never be spontaneous?
Opposite.
Positive delta H and what? Negative delta S. So decreasing overall disorder and taking energy in, so if it's an endothermic reaction, would never, ever, ever be spontaneous. So let's just relate those and reverse it. These two conditions though, so like the positive entropy and the negative delta H are going to yield, and when we do the actual equation, I'll show you in a second, are going to yield a delta G, the Gibbs free energy value, to be a negative number. Okay, so if delta G is ever a negative number, so like negative 50 kilojoules per mole, if I see a negative there, I'm going to automatically assume that that reaction, whatever it was spontaneous. So positive delta S is good, a negative delta H is good, and a negative delta G is spontaneous. So when I mean good, I mean it's going to happen spontaneously or without intervention. So that's one thing we definitely need to relate. I'll come right back here. Other ones, so that's probably assumed. If you have a positive delta G, it's going to yield a non-spontaneous reaction. What conditions would probably be true when that's true? Delta S would be negative, delta H would be positive. Okay, and that's usually what's happening with this case. If the delta G is 0, that means the reaction in the forward direction is just as spontaneous as the reaction in the reverse direction. So neither the forward reaction nor the reverse reaction are favored because the system is probably at equilibrium. And so that's what this whole little at equilibrium thing means. So there are a lot of reactions we talk about are going to be things that are reversible reactions, so you can force them either way with something called the Chateliers principle. Do you guys remember that? The Chateliers, okay. We'll hit that later on. We got time. That's way later. But that's what I mean by at equilibrium. All right, so exergonic and endergonic are two things that are new for us in terms of AP. We don't never really talked about this before. Exergonic is the first one. It's relating to the energy flow into a system or out of a system, just like exothermic and endothermic. But it's talking about the free energy and not just the heat, not just the Q, not just the delta H. So exergonic flows in a direction, the energy is going to flow out. So the energy of the free energy of the system is going to be lowering. So it's still exiting the overall reaction. So, but in the end, it's going to be lowering the free energy of the system. Which is good, because guess who gets that free energy, people? The universe gets that free energy, and that's good, because that's why I say it follows the second law of thermodynamics, TD thermodynamics. So guess what is the opposite? Endergonic. In the end, the energy, free energy of the system will be increasing. So it's like endothermic, except endothermic refers to heat energy, and endergonic refers to free energy, also called Gibbs free energy. So many terms and units. So the free energy of the system is going to go into the universe, and that's what we call good. Okay, satisfies the second law of thermodynamics. I'll give you guys another second there. If I don't finish, I'll just finish my day. It's good. The purple part right here is something that you need to know. It's a phrase that we commonly use. If you say something is thermodynamically favorable, that means it is spontaneous. So thermodynamically favorable is a word that you will want to use any time you have to do an explanation for a type of question like this or anything referring to this. Okay, so thermodynamically favorable means it is spontaneous. AP examiner people last year said they don't want to see the word spontaneous as much because they feel like you guys don't know what spontaneous means. And I was like, you don't know what students. They know what spontaneous means. It means there's with outside intervention. They think like what they've been seeing in the past AP exams is that spontaneous means happens like super fast just all the time. So they felt like people misunderstood the word spontaneous, so they asked us to start using, instead of spontaneous, thermodynamically favorable. So if you ever say the word spontaneous, just know that you mean thermodynamically favorable. If I say that, it means the same thing. It also means something about K values, which don't worry about yet. It's coming soon, but not yet. It's theaters next week. Not next week, like a month from now. But we're going to hit equilibrium, so I'm going to ignore that for now.
Did you say theater?
Theaters, yes, I'm going to say come soon. Theaters next week.
Oh. I was like,
So, and that's all this right here refers to what I just said. So spontaneous means a positive delta G. I just keep, and then this stuff is online too. I don't know if you guys have seen the notes online. Okay, last equation, not quite. Last equation. Same thing as thermal though, okay? Same, products minus reactants, except these values are called delta G values, and they're in the oldest appendix in the book. And you would find your chemicals, go down the list and see their delta G values. And these are called delta G's of formations. I did see that. It's right. And this one is on your reference sheet. So you've got, just like H and S, you can find the Gibbs free energy of a reaction by taking Gibbs free energy of the product summated minus the Gibbs free energy of the reactant summated. So remind me, if this ends up being a negative value, what does that say about the reaction? Spontaneous. I think I just wrote that down wrong on the past slide. Did I write negative or positive? This is a negative. I'm sorry, I just realized. Yes, and that even says it right there too. I just wrote that down. I just said it wrong in my head. Okay, so this is spontaneous, negative value. If the delta G is positive, non-spontaneous, or not thermodynamically favorable. Okay? Okay, this is finally the last one, I promise. This is the one we talked about earlier. But if you're not given a bunch of reactions, or to add up and do your delta G summations, or if you don't have a table, so you can go find the delta G values of the products and find the delta G's of the reactants. If you don't have that stuff, you have to have another way to still calculate delta G, and that is the Gibbs-Helmholtz equation. Helmholtz. You don't have to know the name of it. You just have to know how to write it. Delta G is equal to delta H minus D delta S, which is, relating back to the fact that I said a negative delta G and a positive delta S, dependent upon the temperature, of course, is going to yield, or possibly yield, a negative delta G, which would be
Thermodynamically favorable.
Thank you. I was waiting for someone to say spontaneous. It's hoping that you're right. So, thermodynamically favorable. So if the case was not that, and we had a positive H minus a negative S, what would this yield? A positive value, and that would be non-thermodynamically favorable. So the two driving forces of reactions are enthalpy and entropy. If entropy is increasing, great. If enthalpy is decreasing, great. Thermodynamically favorable reaction will occur without outside intervention. Okay. Who got 50% of that? Okay, this is going. Oh, I'm gonna give you guys some time because I'm gonna give you guys some practice time right now. I might do one problem with you right now.
Please.
Cause I just went. I'll do one problem with you, but because I mean these come in like 15 varieties, so I can do one, but you're still gonna be screwed on the other 14. Okay, you're not screwed. It's just using the information. But I believe it's just I taught this really fast, and I'm gonna have to do some more with this. I just wanted to go through and give you the tools to try some stuff yourself. I pointed out the spontaneous at all temps and non-spontaneous at all temps, but just in case you ever come across just a word questions like, do you think this is going to be spontaneous at high temperatures or low temperatures? If you have a, let's go endothermic reaction, endothermic positive delta H, and you want delta G to be ending up negative so that it's spontaneous, what should this value be?
Positive.
Okay, so it should be positive. Should this be a big T or a large value for temperature or a small value for temperature? I don't know. I'm waiting on you. Okay, so if this right here, you want this positive to minus an even bigger positive number, that T needs to be big. Because if this is like, I don't know, 10 and you want it to minus 100, then the T needs to be a large value, temperature needs to be a large value to yield a negative spontaneous reaction. Because if it was a small value, you might end up with a positive G still. So we have to do some calculations like kind of in our head like that. I'll hit that later. Thermodynamically favorable. I'll hit that later. Okay. I'm not going to do this right now. Let's do, because these are the ones I don't want to do. These are the ones I want to do. Pull out in your packet, your staple packet. Let's do an easy one. Let's start off easy. Well, we get to look these values up, but I am going to go back and do that question because I want to do 20 through 24. So I'm going to go back and do this one first. I'm going to do 24. I'm sorry, I didn't even tell you you're doing. It's called Chapter 16. It says like Entropy Problem Set Chapter 16. It's like a copied page from another book. Do you see it? Okay, I'm going to do that in just a second. I'm going to show you how to set up the question first. If I gave you a situation where I said, I want you to tell me at what temperatures will this process be spontaneous, you would have to set up an equation like an inequality. Because if I want this value to be spontaneous, or this value to represent a spontaneous reaction, would that be positive or negative? Negative. So if delta G is equal to delta T minus T delta S, then pretty much what I want is if I can set this right here represents delta G. Yes, because they are equal. If this represents delta G, I want delta G to be less than 0. Does that make sense? I want delta G to be negative, so I want it to be less than 0. So if this equals delta G, and if I have numbers for those, or if I'm identifying something from this subset of subvariables, which is T in my case, I need to set 0 to be greater than delta H minus T delta S, which is delta G in this case. So how would I rearrange this equation to solve for T? I know you can see it, but tell me how you would do it. Plus T delta S to both sides. So then you have T delta S is equal to delta H divided by delta S divided by delta S. What if delta S was a negative value? What would that do to the inequality? Flip it. You remember that from like, I don't know, algebra 1, algebra 2, math 1, math 2? Okay, so that cancels there, and that would leave me with T is greater than delta H over delta S. That's what we're going to do with number 23. You ready? I lied. 24. 24. What does that say? 24 say. At what temperatures will the following be spontaneous? Great. Okay. At what temperatures will it be spontaneous? Will delta G be negative? So according to the first one, we've got negative 18 kilojoules and negative 60 joules per Kelvin. So we're going to find this in Kelvin. if your equation is delta G is equal to delta H minus T delta S, I'm going to go ahead and solve for T, like set it up. Well, no, I'm not. I'm going to show you the full way first. If you want this right here to be negative, you're going to do the same thing like I did previously. 0 is greater than delta G. Delta G is equal to delta H minus T delta S. I'm going to plug in my numbers like they gave me, which was, what was the delta H? 18 what? Kilojoules. Minus T, which I don't know. S was given as? Okay, so you know it's a kilojoules and joules, right? What do you want to do with that? Either change that to kilojoules or change that to joules. I'm going to change this one to joules to I like joules better. So I'm going to put 18,000 joules here versus 18 kilojoules. And then T, what did you say it was? Negative 60 joules per Kelvin. Yeah.
Is this supposed to be part A, part B, part C, or is this multiple choice?
This is part A.
Okay. I was like, are you supposed to look for? Okay, never mind. I got you.
Okay, so all I'm going to do is add over, so then T, that's a negative still, negative 60 joules per Kelvin is equal to negative 18,000 joules. Solve. If I added it, so if I add T delta S to that side and other side, that's gone. But I'm leaving the negative there for what's there. Okay, and this is not equal. I keep doing that. This is still greater than. So negative 60 joules per Kelvin divided by negative 60 joules per Kelvin. So then what do? T is less than, right, I'm flipping my sign right here. T is less than 300, no, yeah, 300 Kelvin. So if T is less than 300 Kelvin, the reaction is spontaneous. What if it was 301? It would yield a positive delta G when I did the math. And that would be bad, not thermodynamically favorable. Okay, that's the only one I'm going to set up right now. So you guys can work on the rest of 24, because it's not multiple choice. Work on 23. You can do 30. You would need a book, though. You would need a book for a couple of these, really, for some values. So you can, let's start there, and I'll tell you what else I want you to do. 50, you're going to have to do an alternate equation, not this one. But you do, and I have my book if you want me to post it up here, but you're going to be flipping back and forth. So try to do them without a book first. What's up? What? I'm gonna stop.